Swayam Prabha. Digital India. Educated India.
Good morning. We are going to continue our discussion of linear instability analysis. Towards the end of the last class, we had derived a set of linearized governing equations. So, let us start by looking at the linearized governing equations, and our first job is going to be to define a set of boundary conditions that can go with these linearized governing equations. Okay. So, we will make that our job for today. Okay. We took the complete two dimensional Navier-Stokes equations and Euler's equations, and after scratching out the terms that are going to be order epsilon and epsilon, after scratching out the terms that are order epsilon squared and only keeping the terms that are order epsilon being the order of the perturbation quantity, which are the primed quantities. So, essentially only the part that is linear in the primed quantity. We now have a set of equations that will tell us what the behavior of the primed quantities is in time and space. Now, from these, so this is basically like saying these are the equations that govern the growth or evolution of the disturbance as the evolution grows in time. But as what we want is always go back to our analogy of ball in a cup. Okay, so, if I take the ball and move it slightly to the left from its bottommost equilibrium position, I can write a set of mechanics equations that describe the movement of that ball from this perturbed position. So, that is essentially saying the force imbalance due to the slight perturbation in the position of the ball in that cup is going to result in an acceleration, and if that acceleration happens to point towards the previous equilibrium position, that is a stable equilibrium. That was the that is our essential understanding of stability. These equations 8, 9 and 10 here essentially govern the growth of those perturbations, or really not even the growth, the change of those perturbations in time and space x and y. Now, what we want to do is impose a sinusoidal perturbation on the meniscus itself, on the interface between the two fluids, and we started to say that we are going to make this meniscus have a function of the form cosine 2 pi x over lambda times e power omega t times eta 0. The 2 pi x over lambda essentially tells us the functional form of a wave that we will impose on the free surface, and watch it either grow or decay in time, and the growth or decay is going to be determined by the real part of omega. If omega r is greater than 0, then the wave amplitude grows in time, because the amplitude is this eta 0 times e power omega t, and the imaginary part of this wave number of the growth rate essentially creates another sinusoidal motion in time. So, if I take a wave, and if the wave is, say for example, simply going up and down in time just like that, that would involve no imaginary part to the omega. If the wave is also doing this, like all waves do, there is a motion of the crest in time to the left or to the right. There is a wave speed associated with that crest. That wave speed is given by this omega I and k, the wave number put together. Okay. So, as far as the actual stability, whether the thing grows in amplitude or decays in amplitude, is only determined by the real part of omega. Okay. And then we made one small distinction that said, say for example, k in this equation here is real, meaning k is a real wave number and omega is allowed to be complex, and that in turn gives us the real part of that complex number gives us the actual growth of the amplitude in space. So, this kind of an instability analysis is called a temporal linear instability analysis, where we impose real spatial waves. I will even put that, we will impose real spatial waves and watch their behavior in time. The other possibility is to impose a wave in time, say for example, at some inlet location I have a small perturbation that I can add to the time component and watch what that small time perturbation does over space. Okay. We will leave that out of our argument for now, but essentially this is our discussion. Now, we have chosen to impose a disturbance on the meniscus. Remember, just for clarity, I will say y equal to 0 is the unperturbed free surface. So, on top of that unperturbed free surface, we have added this disturbance. So, essentially you might think of this as 0 plus this, just as everything else that we have done was the mean flow plus the small perturbation. In this case, the mean interface location is y equal to 0. So, eta 0 is an order epsilon quantity. Okay. So, we will need to be aware of that. So, now we need the next order of business is to define a set of boundary conditions. Before that, we will quickly make a list of all the variables that we have, u I prime, v I prime, p I prime, each of this for I equal to 1 or 2 and eta 0. Eta 0 is the amplitude of the disturbance. So, as far as u I prime and p I prime is concerned, we have 3 equations in the form of 8, 9 and 10. Now, remember these are still subscripted in I, which means each one each of these for I equal to 1 and 2 gives us a total of 6 equations for the 6 variables. The eta 0 is an interface condition, it is not necessarily an unknown quantity, it is what we are imposing, okay, and we just want to watch its growth in time, right, or this is like an initial amplitude of the disturbance. Let us be more specific. Okay. The first set of boundary conditions is what we will call kinematic boundary conditions. So, let us quickly see what that is. I will redraw our sketch from the earlier page here. just take the condition, the mean flow condition, that u equals capital U2. So, now I have imposed these surface waves on the free surface, and the liquid, if I take a liquid particle right on that free surface, so this is a particle that is on the perturbed free surface. As this fluid flows this way, the wave itself is going to be moving with the fluid. Because of that, the fluid has, because a fluid particle, let us say this is the next time position of the same wave, what was here is now here, just because the wave moved. This is the previous time position, this is the next time position. Now, as the wave reaches its crest and comes back down, this particle which is at that free surface is only going to go up and down. Okay. So, the first set of boundary conditions, which are called the kinematic boundary conditions, basically say that the y direction velocity of the particle is given by the rate of change of eta plus u d eta dx. Okay. So, this part here is the co-moving derivative of eta it is a co-moving derivative of eta, and what we say is even if eta is not a function of time. So, think for a moment, remember we said eta is this is our eta as a function of this whole thing as a function of x and t. So, even if eta, even if let us say this omega was 0, just by a wave moving now at a velocity u I, okay, you get an up and down motion which is V I. Okay. So, if I ignore the first term here called d eta dt, the partial derivative of eta with respect to time, if I ignore that for a moment and only take the second term on the right hand side here, u I times d eta dx is saying that the rate of movement of a particle in the upward direction is essentially governed by the x direction movement of the velocity and the slope of the interface. So, if the interface has a certain slope and it is moving this way, then a point on that meniscus is essentially like it is being pushed upwards with a velocity u I times d eta dx. D eta dx is the local slope of that interface. If on top of this, if the wave amplitude itself is growing, that is further additive y direction velocity. So, I get two kinds of y direction velocity at that free surface. One is no growth in the amplitude, just movement of a sloped meniscus, in this case a wavy meniscus, and the second kind is where the growth there is, like this is the meniscus, it is just growing in time. So, the trough is coming down and the crest is reaching for higher values of y. That in itself means that there is a y direction velocity. That is that part of the y direction velocity is represented by the first term on the right hand side. If I had this wave on the free surface and if I was simply observing a point on the free surface, that point as this wave moves, that spatial location shows an upward y velocity. That is represented by the second term on the right hand side. The total y velocity at any point at any x location on the free surface is given by the sum of these two. Okay. Now, there is still one issue. If I take the ui and do our perturbation plus the mean flow plus the perturbation substitution, that part there again happens to be order epsilon squared. Okay. So, what we end up is V I prime at y equal to 0. So, the actual velocity, now we will come to this in just a moment. Now, remember we are talking of the fluid velocity on the meniscus, right there. This fluid particle used to be there, now it is here and now it is down here. So, at this x location there is a negative y velocity because the slope is negative, okay, with no d eta dt being positive, right. Now, ideally I am evaluating the V I velocity on the meniscus. So, this velocity in this equation is the upward velocity on the free surface. Okay, which is, if I was to represent that mathematically, V I at y equal to eta. Eta is the free surface itself. V I at y equal to eta can be written as V I at y equal to 0 plus eta times dvi dy evaluated at y equal to 0 plus, this is simply a Taylor series expansion. Okay. If you notice again, this part here is order epsilon squared. So, just as we simplified the right hand side of this equation to only have order epsilon terms, if I simplify the left hand side to only have order epsilon terms, then V I at y equal to eta can be replaced by V I at y equal to 0 or V I prime at y equal to 0. So, ideally we want V I prime because V I prime is the only upward velocity, there is no mean flow that is in the upward direction. So, therefore, this is again ideally I should have V I equal to d eta dt plus u I dx and V I is equal to 0 plus V I prime. Okay. So, we can drop the 0 plus V I prime, because we have now sort of looked at this enough to know that the mean flow is 0. Okay. So, if I take the last part, this V I prime is actually the perturbation free surface velocity at the free surface at y equal to eta, but that can be substituted by taking V I prime at y equal to eta is equal to V I prime at y equal to 0 to order epsilon. If I have to include the higher order term, sometime later, that is up to order epsilon squared, but as far as a linear instability analysis is concerned, I am only going to keep terms that are order epsilon. So, we have the governing equations 8, 9, 10 to go with. I have this boundary condition 8, 9, 10 to go with that. I need this boundary condition, let us get to that. I need this free surface condition 11 and this condition 12. Now, mind you, equation 12 has two possibilities. For I equal to 1 and I equal to 2, meaning I have the same meniscus d eta dt, but depending on the fluid I am in, the upward velocity of that fluid is determined by the balance from whichever direction I take that blue particle argument. Okay. So, whether this blue particle was in the I equal to 2 fluid or I equal to 1 fluid makes no difference, as long as the free surface, I am able to imagine the free surface is composed of 2 fluids, one on top of the other, and whichever fluid I look at, it does not matter, this condition has to hold. Okay. Now, the second set of conditions is called a dynamic condition. What do we mean by that? If I go back to this same diagram, if I imagine for a moment that let us look at the mean pressures, capital P I, or will be specific, capital P 1 is equal to capital P 2 equal to 0 by definition. That is where we left off. So, we found that for a flat free surface, capital P 1 is the mean pressure in the entire fluid 1, capital P 2 is the mean pressure in the entire fluid P 2. This pressure cannot vary with x and y, we found that from the equations, and then once I know they are constants and they are both equal to each other, I have the freedom to set that to any value, we set that equal to 0. So, now that I have a curved interface, the red line here in this figure, the perturbed versions of these pressures do not necessarily have to be equal. So, if I take P I prime or P 1 prime is the pressure on the fluid above, P 2 prime is the pressure in the fluid below, right. That is what already appeared in the governing equations in the governing equations 8, 9 and 10. Okay. So, if this P1 prime and P2 prime are now functions of x, y and time, if I take an arbitrarily small element of fluid just like that and draw a free body diagram of it. So, I will expand that out. There is pressure P1 prime on there, P2 prime on the other side, and there is a surface tension force. Okay. So, because I cut out a small element of the fluid, the rest of the fluid exerts a force on this small element due to surface tension. Okay. So, if I write a force balance here, we can see that P1 minus P2 sigma times kappa. So, this kappa is basically the fluid is the meniscus curvature This free surface curvature essentially dictates the difference in the forces between P1 and P2. So, just to understand this, we will go back to just a simple curved free surface. If I have a pressure P1 acting here and a pressure P2 acting on the other side, you can see that this infinitesimal piece. So, I am now looking at a little infinitesimal piece of fluid. If I take this infinitesimal piece of fluid and let us say it exerts a small angle delta theta, this infinitesimal piece of fluid exerts a net, there is a net force at this point in the magnitude